and it's an analog input. But instead of using an analog channel directly, you can just use the Gyro class, which handles all the math and conversions for you. Sorry, this should be Gyro. You pass in the channel of the analog input, and then it's got a number of functions like getAngle, which basically returns the angle in degrees. It's a float. Reset, which will reset the angle to be 0 at wherever it's currently pointed. And then, very importantly, for the gyro, you have to set the sensitivity, which determines how the degrees are scaled. So if you set this wrong, you might find that a complete rotation is actually 400 degrees or something like that. Lastly, there's the timer, which, as I mentioned before, allows you to have real-time control of the robot. So if you construct an instance of the timer and call start on it, once you call get, it will return the number of microseconds since you hit start. So you can use this to time autonomous modes. There are also a bunch of other classes, which I won't go into details on, but there's classes for the accelerometer, for the Hall effect gear tooth sensors. There's a class for a magnetic digital compass, and there's also ultrasonic rangefinder sensor class. Next up, Lee is going to talk a bit about the camera.
John? The gyro class, I noticed that there was no method for the gyro bias. That's the reason why that is not the word bias.
Yeah, the bias is handled.
Right now, the bias is handled by the constructor of the gyro.
So if I auto-calculate some bias, it may not be doing so.
Yeah, it's.
Sorry, the issue is that on any analog input, there's a bit of noise, twittering, and there's no dead banding around it to get rid of that. So if it twitters a little bit more one side than the other, it just starts taking off now.
Great. So after we just had that long story on C++, we're going to the camera, which is written in much more C than C++. Now, I'm not sure what the mental experience is here. Some of you may have used the CMU cam in previous years. Others may have never used the camera in FRC before. Basically, what we use the camera for is identifying a blob of color. It may be light like what we have up here. It may just be a passive target. It depends on what the game design committee wants to use this year. As Carly said before, it's because they worked it up, it's very likely that the camera will be used in the game this year. So we have the camera, we use it to track some sort of target. The target might be to try to find where the goal is or where you have to go. It works with groups of things called particles. A particle is basically just a blob of pixels. I'll go deeper into that later. So basically the primary use of the camera is you can either track a colored target or it can also identify the size of colored targets. Now the particle is the main useful data that we use from the camera. What I'll be explaining here is just everything on how to use particles. There are per pixel functions on the camera, but we haven't found a use for it with the testing we've done, but we don't know if we'll need it for the actual game this year. So as I said, a single blob of color describes the image of anything a light colored object that the GDC wants. Now particle has a few things about it that you need to know. So the first thing is the center of mass x and y. That's going to be the most useful part of the particle you will have. That basically says where on the camera screen, or on the image coming from the camera, where is this particle located? So what's the weighted average of everywhere of this blob of color that we're looking for? It also has the surface area, rectangular bounds. You can use those to decide how large is the particle. You can use that if you have multiple particles. You can use that to rank which particle you want to operate with. Also, just a few more things. Percent of the image, if you want to see relative to the size of the image. Particle quality is a high particle quality will mean that there's no holes in the particle, or it's solid and it's mostly the same color. So the first thing we need to know and how to find a particle of a certain color is how do we define a color? What we were using is HSL. So this stands for hue, saturation, and luminosity. Some of you are probably going to cringe when I describe this, but it's very simplified. The hue is a pigment of color. So the hue is how red, how blue, how green is the color. The saturation is how much that color applied to, or how much of this hue is being applied to the final color. So is this a very vibrant color? Can we see the color very well? Or is it kind of grayed down, kind of shadowy? The luminosity is finally how bright the color is. So if you have a full luminosity, the color is just going to be white. If you have zero luminosity, it's just going to be black. If you put it somewhere in the middle there, it's going to make it either like a dark color or a bright color. So luminosity will control the difference between pink and red, for example. So going into some of the code, the first thing you have to do is you start the camera task. The camera, first thing that you do with this is you fork the camera task. What this does is because the compact Rio's full operating system, you have multiple tasks running at the same time. So when you do this, the camera doesn't make your own program lag. So we start the program task. The reason why it's in this statement here is it lets you know if it failed for whatever reason. So if the camera's not plugged in or if it's not operating properly, this will throw and you'll get a log error on why the camera isn't working. The next thing to do is you have to set your target. So we have this thing here called tracking threshold data. We'll get into that a bit later. So what this does is it sets tracking data to green and passive light. So what this is doing is using WPI's definition of what passive light and green is. Now, if you don't like what WPI defines green to be, then we can pick our own custom colors. So after you define some threshold data with WPI's vision system, you can say, well, their color may or may not be exactly what we're looking for. In our case, our active light was not the same as their passive light, so we have to set our own values. So what we do is we have to choose a range for hue, saturation, and luminosity. So here our range was just from 64 to 114 on the hue. So that defines a range of colors. That's roughly just the green part of the spectrum. Saturation, so it's 161 to 255. These are all in ranges from 0 to 155. So saturation is 161 to 255. Because we're tracking an active light like this, saturation is going to be pretty high because it's a very intense color. And the luminance is kind of lower here. The problem we found with the active lights is that when you first turn the light on, it seemed, if you view the camera, it would seem like there's a white blob in the middle, followed by a green outer rim. We have to track that green outer rim because if we just look for that for everything or the white blob, it can track onto one of these lights and we had some problems with robots driving wherever they wanted to. So now that you've defined a particle, how do we get the particle and how do we use the particle? So first thing we do is these defines up here. This is just saying that we use this in a little bit. We're saying it has to be between 0.25% of the image and 10% of the image. So if more than 10% of the image coming back from the camera is occupied by this light, that means we're just standing in front of it or something and we can't get any useful information from it. And if less than 1/4% of the camera is this green color, then it's probably not the light we're looking for. So what we do is we find the data and that passes it into our threshold data, hue, saturation, luminosity, and that will return a particle analysis report. So now what we're looking at is if that particle analysis report, it has that total image percent that I was talking about before. If that is, so we have to see if it's within our range of how large the particle is allowed to be. Now, in the situation that it does occur, that means we've found a light, we have a position on it. We'll take that analysis report and we'll do something with it. So here we're taking the center of mass x and y normalized. That just means that it's the center of mass on the camera and they convert it between a value of -1 and +1. And we'll just print it to the screen for our uses. So that's the presentation on how to program the row of C++.
I just wanted to mention that if any of that didn't make sense to you, don't worry, because this afternoon we're going to be demonstrating it on a real live robot. Yep? Yeah, this will be all up on the first forum.